Today, we'll be talking about capacitance. A capacitor is a device where two conductors with charge of equal magnitude and opposite charge are separated by a distance. Capacitance is the ratio of charge on either plate to the potential difference between them. The capacitance of two parallel conductive plates is C equals epsilon naught A over D. A is the area of the plate, and D is the distance between them. When the capacitor has a non-conducting material between the plates, the capacitance is changed. It's multiplied by a dielectric constant, which is a property of the material. The material is called a dielectric. In our first example, we'd like to know how much charge can be placed on the plates of a 1000 microfarad capacitor by a 12-volt battery. Then, how large a voltage would be required to place the same charge on a 1 microfarad capacitor. We know the capacitance and the voltage, so we can multiply them to find the charge on the plates. Multiplying through, the charge on the plates is 1.2 times 10 to the minus second coulombs. Now we would like to know how much voltage would be needed to place the same charge on a 1 microfarad capacitor. Plugging in our known value for charge and the capacitance of the new capacitor, we find that we would require a voltage of 1.2 times 10 to the fourth volts. In our second example, we have an empty 25 microfarad parallel plate capacitor charged with a 12-volt battery. The battery is then disconnected, and the region between the parallel plates is filled with pure water, which has a dielectric constant of 80.4. What is the capacitance, charge, and voltage for the water-filled capacitor? We can start by finding the new capacitance of the water-filled capacitor, but we recognize that epsilon naught A over D is just the capacitance of the empty capacitor, so we can substitute in C empty being the capacitance of the empty capacitor. Multiplying the dielectric constant and the starting capacitance, we find that the water-filled capacitor has a new capacitance of 2.0 times 10 to the minus third farads. The charge on our capacitor will not have changed because the battery has been removed. The charge will be whatever the charge was before the capacitor was disconnected. Using our old capacitance value and the voltage of the battery, we find that the charge on the capacitor is 3.0 times 10 to the minus fourth coulombs. The new voltage across the capacitor's plates will be the charge divided by the new capacitance. So, we plug in our value for charge and our value for the new water-filled capacitance to find that the new voltage is 0.15 volts.